Okay, so guys, we're going to start chapter 8 here, and the first thing that we're going to talk about is the average value of a function, okay? Now, when you think about average value, we're kind of thinking about the average height of a function. So, for example, like a question might be something like, hey, I turn my thermostat on in the morning, and it's at 70 degrees, and then it heats up until it gets to 80, and then it gets down, it gets cooler until it gets to 50, and then it's back up to 65. And what's the average of all those heights? Okay, it's kind of like that line through there. So it says to draw a horizontal segment from A to B in the figure, which could represent the average height. So, well, just on this little section, I don't know, I feel like it would maybe be right there, would be my average height. Okay. And it says to find the height of the rectangle formed. Well, you guys know rectangle is base times height. The base is the width of that rectangle is B minus A, because it's wherever I start, wherever I finish, right? So the base of that is B minus A. Okay, times whatever this height is, and that's the rectangle. All right. Okay, so the area of the rectangle should be equal to the area under the curve, the closer we get to that, right? So for example, let's say this is my area under my rectangle, and then look, how close is that to this actual area right here? So a little bit from, down here comes up over there, and it kind of averages out. So that's the idea, okay? So now that we know that the area under the curve, which is the integral from A to B, is the width times the height, okay? And now solve for the average height. Well, all I would do to solve this, all right, is I would go ahead to get height by itself. I would divide B minus A over. That's my average height, or my average value right there. Okay? So when you look at here, it says, okay, so the average value on an interval A to B is the integral from A to B, the area divided by the width. And the area divided by the width gives me the height. Usually what I do for average value is I put this out in front. So that's how I memorize average value, is I memorize average value has the 1 over B minus A in the front of the integral. I just memorize that and we're good to go. Really important that in order for this to work, F must be continuous. K can't be something that, has an asymptote in the middle or something like that. Okay? So the questions are really quite this simple. Find the average value of this curve on the interval 0 to 2 without using a calculator. Okay? Well, all I do is I go 1 over B minus A, the integral from A to B of this curve. And then I just figure that out. So it's just the same integral problem that we always have. It's just now I have this 1/2 out front. Okay? I usually just keep that out front. The integral of x to the third is x to the fourth over 4. The integral of x is x squared over 2. I'm evaluating it from 2 to 0. Again, I'll still keep the 1/2 out front. And when I go to do top minus bottom, okay, 2 to the fourth is 16 over 4. 2 squared is 4 over 2. And then when I plug in 0, it's just 0 minus 0. Okay? So my final answer here is, so it's 1/2 times 2, which is 1. So really, if you think about what that's telling you, the average height of this, I could have made that look a little better. Hang on. The average height of this is at 1. If I were to take all the heights here, the negative heights, all the positive heights, it's right about at 1. Okay? Now it says, use your calculator to find the value of C in the interval where C equals the absolute value, the average value found in example 4. Okay, so here's the average value. So what this is saying is that there's some point, all right, where this equation will equal the average value. And this is not something that we can do by hand, this particular one. We do have to do this on our graphing calculators. So, whoops, let me get my graphing calculator up here real quick. And let's take a look. All right, cool. So the graph that I was looking at was x to the third minus x. And I want to see at what point it actually equals that average value of 1. So if I graph this, all right, and remember, we're kind of focusing just from 0 to 2, okay? And so if I, I could actually look, I could do a zoom box because those are kind of fun. 0 to 2. Oh, shoot, I have to actually use my cursor, don't I? Okay, let's try this again. Enter. Let me just see if I can make a little bit of a better picture for us. Okay, so kind of just look at that little section right there. In that little box, right, that's the average height of the curve. And so right here is where it equals its average height. Okay, so I just kind of want you to focus on that part. All right, so right now, let me go ahead and actually get rid of that and just say calculate the intersect between these two. And I get 1, 2, 3 equals. The intersection is 1.324. All right. So what this is saying is there is some number C where it actually equals the average height. So let's say this was like a temperature reading or something like that, and this was like time or whatever. And I'd say at time 1.324, it's the average of all the different times that it will be the whole day. Okay. So pretty straightforward stuff, right? Okay, this other one's not as straightforward. In fact, I don't even know that we teach this in AB, maybe. I didn't teach it last year. It's one of the lesser known topics, but we can definitely talk about this. Arc length formula, okay? So find the length of the arc from example 4 on the interval from 0 to 2. So what this is asking me to do is to find the arc length. Basically, we're just looking at this random formula that's going to allow me to find the length of that, okay? And the formula is the integral from a to b of the square root of 1 plus the derivative squared. All right. And it sort of looks like, what the heck, this just hits me out of nowhere with no, like, context. Yeah, I'm going to say this just kind of hits us out of nowhere with no context, right? We can look into this a little more as a proof of where this arc length formula came from, but this is what it is. So if I take the derivative, which is 3x squared minus 1. I put it right here. And then how am I going to do this? Well, I can just use a calculator for that too. So I'm going to go, let me go out to the home screen. Let me go math 9. The integral from 0 to 2 of the square root of 1 plus parenthesis, I'm going to put the derivative in here, 3x squared minus 1. Parenthesis, and then go out here, put in my dx, and there we go. Okay? Oh, shoot, I did that wrong. Hold on. I wasn't looking at my formula careful enough. Inside the square root, the derivative is squared, not the 1 plus, just the derivative. There we go. That's what you want that to look like. All right, so that's going to give me 7.413. Okay, for my arc length. I definitely have a feeling that this comes from a squared plus b squared equals c squared, and the square root of that, that's my guess, is that it comes from something to do with the, a squared plus b squared equals c squared, like triangle or something, but then finding that. Anyway, so we'll have to look into that. Pretty cool. Okay. The last thing is the accumulation of rate functions. So this is kind of what we're talking about, guys, when we talk about the SPAN method, right? Start plus accumulation. An integral is an accumulation of a function. So it's talking about in 4.1 is when we first talked about that. Okay, the graph at the right models the rainfall in inches per hour from midnight until 6 a.m. So time 0 is midnight, and then this is 6 a.m. All right, during a tropical rainstorm. Write a complete sentence to explain what point A on the graph represents. Now look, you guys, the y-coordinate is the rate of rainfall. All right, in inches per hour. So what does that tell me? Well, point A says at 3 a.m., the rain is falling at a rate of, yeah, look at here, 1.0 inches per hour. Okay? At 3 a.m., the rain's falling at a rate of 1.0 inches per hour. And it just says to make sure that we include numbers or units in there, so we did. Okay? What is the slope of the graph between B and C? The slope. Okay? Well, this goes down 5 over 1. Now, my tendency is to just be like, oh, down 5 over 1. Okay? Be careful of the way that they're labeling your graph, because that's what I was just about to do. Down 5 is really down 1 inch over 1 hour. So it's actually not down 5 over 1, it's down 1 over 1. Okay, so it's -1. But it wanted me to include, oh, I didn't have to include units on that one. I want to talk about it anyways, though. It said to include units on 8 and 10 and 12, but I want to include units on this one. Okay, you guys? Look, we're basically taking, when we're finding a slope, we're doing a y2 minus y1 over x2 minus x1, and the y values are in inches per hour, and the x values are in hours. And so when I do a slope, it's almost like a derivative, right? I mean, it is a derivative. It's in inches per hour. Or you are allowed to say inches per hour squared. Okay, so we're going to start talking about like word problems and doing stuff like this. All right. Write a complete sentence to explain the meaning of your answer. So what's the meaning of the slope of this? Inches per hour. All right. Oh, shoot. Actually, hold on. Example 7. There we go. So it says between, let's see, it started at point B, 4 a.m. and 5 a.m., right? The rate of rainfall is decreasing by 1 inch per hour. Or you could say is increasing, I don't know, I like this will explain it a little bit better actually. Is increasing or is decreasing at a rate of, I kind of like that because then guys, look, you have the word, the rate of rainfall is decreasing at a rate of, so it's a rate of a rate, which is why it's inches per hour squared, which is kind of how we do that. Okay? All right. Same little graphy guy here. What is the integral from 3 to 5? Okay, guys, that's pretty easy because we could just find an area. You could do a trapezoid, or if you guys want, we could do a rectangle and a triangle, which is probably fun, right? So let's see. If I do this triangle right here, that'll just be base times height. The height is 1 inch. The base is 1 inch, so that's 1. And then this is 1/2 base times height, so it's 0.5. So this is like 1.5, okay? Now, an integral is going backwards, right? So this is 1.5. We could also call that 3 over 2. Write in a sentence to explain the meaning of that. Okay, well, it's an accumulation. So if I was going inches per hour and I was going forward, like taking a slope, I'd do another per hour. But I'm going backwards, which means I erase an hour. So guess what? It's 1.5 inches, okay, of rainfall between 3 a.m. and 5 a.m. This idea is like super, super important. The idea of an area being an accumulation, especially when you're taking an area of a rate graph, all right? So this is the rate of rainfall, and between this time and this time, if I find the area under the curve, that is the accumulation of rain from 3 a.m. to 5 a.m., okay? Okay, last part is let's approximate the value of the integral from 0 to 6 using geometrical regions. Let's see. I mean, do we need to do 2 different triangles, or can I just do I think I could just do 1 triangle. That looks like that's going to approximate that rather nicely, actually. Okay. And remember, we just found out that that one was 1.5. And then if this is 1/2, the base is 3, the height is 1. So that one's actually also 1.5, that triangle, which will approximate it nicely. And then up to 6, guess what happened there, guys? It stopped raining. That's 0. So it's a total of 3. Now, again, we're doing an integral of a rate. So inches per hour goes backwards to inches. Okay. So 3 inches is what I got. And I just did a triangle plus a triangle there. And then it was from midnight to 6 a.m. there was approximately 3 inches of rainfall. Okay, an accumulation. That's it. Start for chapter 8. Not too bad.